Welcome to lecture number 4 for ECE 463 Modern Control, Eigenvalues and Eigenvectors. Now back when you took linear algebra, eigenvalues and eigenvectors were probably defined as follows. Eigenvalues are the determinant of lambda I minus a equals 0, and the eigenvectors are the vector capital lambda, such that a times lambda is your eigenvalue times the eigenvector. That's the definition. But so what? What does it mean? One of the problems they have in math is they have to keep it very general. The advantage of this class is we can look at specific examples, such as a circuit or a heat equation, and show you for electrical engineers what is an eigenvalue, what is an eigenvector. So hopefully at the end of this class you'll actually understand them, which puts you way ahead of most people. Very few people understand eigenvalues and eigenvectors. Hopefully, you'll get some feeling for what they mean. What eigenvalues tell you is how a system behaves. What eigenvectors tell you is what behaves that way. So if you can look at a system and look at the eigenvalues and eigenvectors, you not only know how it behaves, but which part of the system behaves each way. I'll go through a couple circuits to illustrate that. So let's start out. The RLC circuit that we looked at in our last lecture is as follows. I've got two inductors, two capacitors, and two resistors. The energy in the system is defined by the current through the inductors and voltage across capacitors. So I'll make the states I1, V2, I3, and V4. And the dynamics turns out to be as follows. I've got my x dot equals AX plus BU. So here's your state transition matrix, your A matrix, that tells you how the energy moves about the system. Now, if you went into MATLAB, input the system as your A, B, C, D, find the transfer function, you'll wind up with this. So this is what we wound up with back in lecture 3. So the output, which is the voltage on the second capacitor, B4, is 2500 over 4 poles. Well, that's related to the eigenvalues. If you take your A matrix and find the eigenvalues, turns out the eigenvalues are your poles. So likewise, eigenvalues are all important. They tell you what the poles are. Poles are all important. They tell you how it's going to behave. From the poles, it tells me, here's my dominant pole, the settling time is about 8 seconds. And here's another set of poles. In addition, there's another pole that's not quite the same as initial condition, a little bit smaller, because it's further from the origin. But it's going to decay in about 10 seconds while oscillating at 8.67 radians per second. So that's the eigenvalues. Again, eigenvalues are poles. That's how the system behaves. But what eigenvalues don't tell you is they don't tell you what behaves that way. So we know that something decays at e to the minus 98t, something oscillates, and something decays at e to the minus 0.5t, but I don't really know what. And to illustrate how the eigenvalues tell you how it behaves, take the impulse response. If I have the system Y and my input is an impulse, a big snap, the response is going to be the Laplace transform of an impulse, which is 1, times the transfer function. Do your partial fraction expansion, and what you wind up with are 4 terms. So again, the eigenvalues are telling you how it behaves. Eigenvectors tell you what behaves that way. The transient response is going to look something like this. It's going to be something e to the lambda 1t, e to the lambda 2t. Those are the eigenvalues. I know I have 4 eigenvalues, so these 4 contribute in some way to produce your response. The eigenvector, each eigenvalue has an eigenvector. The eigenvector tells you the mode shape. So something with this mode shape plus the second mode shape and so on all add together to produce the output. And your constants A1, A2, A3, A4 are how much the different eigenvectors are excited. At t equals 0, e to the 0 is 1. So at t equals 0, I just get x0 is something times lambda 1, something times lambda 2. All the eigenvectors added together give you the initial condition. Or in matrix form, the initial condition is your eigenvector matrix times your constant. And this is just your A1, A2, A3, A4. Or the constants are just the inverse of the eigenvector matrix times your initial condition. So the eigenvalues again tell you how the system behaves, the eigenvectors tell you what behaves that way, and the initial condition tells you which eigenvectors are excited and how much of each eigenvector is involved in the initial condition. So to illustrate that, let's look at the eigenvalues and eigenvectors. That's previous circuit. Again, I've got 4 eigenvalues. In MATLAB, if I just do EIG, it gives you the eigenvalues. If I return 2 parameters, it gives me the eigenvectors and eigenvalues. And the reason they do that is very few people understand eigenvectors. But for those people that do, they do tell you quite a bit. It tells you what behaves that way. So each eigenvalue has an eigenvector. For example, something decays as e to the minus 98t. The eigenvector tells you what behaves that way. So this is your I1, V2, I3, V4. If we make the initial condition primarily I1 and V2, that's going to decay as e to the minus 98t. Something oscillates. That's this eigenvector. And for oscillating system, I have sine and cosine. If I take the real part of the eigenvector, that'll give me a cosine. The complex part, that gives me sine. So if I make the initial condition in the first column, primarily V2 and V4, then the energy is going to bounce between those two, oscillating at 8.67 radians per second, decaying as e to the minus 0.37 t. But look at the complex part, that's primarily just I3. If my initial condition is primarily I3, again, the energy is going to bounce back and forth between the two inductors, between the two capacitors, as the eigenvalue. There's also a slow mode. If I make the initial condition right here, so that instead of the voltages being opposite each other, they're both the same, 0.7, then that's going to decay slowly as e to the minus 0.5t. So that's what the eigenvectors tell you. It tells you what behaves that way, and the eigenvalue tells you how it behaves. So, just for fun, let's look at making the initial condition the fast eigenvector. In that case, the response is going to decay as e to the minus 98t. And the reason for that is going back up here. If my initial condition is the first eigenvector, lambda 1, then all the other terms are 0, and only a1 is non-zero. So only the first mode is excited, meaning only this term appears in the output. And you can see that if I make this my initial condition in MATLAB and simulate it, which in MATLAB is I've got my A, B, C, D matrix. For an impulse response, I would just make the B matrix my initial condition. And then find the impulse response of that system given x0, that's my B matrix. This is the response. This is decaying as e to the minus 98t, very quickly decaying. It decays in about 50 milliseconds. No oscillations, real pole. If instead I make the initial condition the real part of the second eigenvector, what I wind up with is same thing as before, just change the initial condition. Now, this decays as e to the minus 0.37t, takes about 10 seconds to decay, and oscillates at 8.67 radians per second. So that's the real part, that's your cosine function. You can notice it starts at a peak. If I make it the complex part, that's a sine function. Again, same eigenvector, decays in 10 seconds, oscillating 8.67 radians per second. Plus, there's the slow mode, eigenvalue at minus 0.5. If I make that my initial condition, it decays very slowly, takes about 8 seconds to settle out as a real pole. Finally, if I make the initial condition something random, like all ones, what that's going to do is that'll excite all 4 eigenvectors. If all 4 eigenvectors are involved in the initial condition, then they all decay according to their eigenvalue. The fast mode quickly goes to 0, leaving me with the slow mode at minus 0.5 and the oscillatory mode. So that was for the 4th-stage or the 4th order RLC circuit. Let's look at another example. This is a 10-stage RC filter. From lecture number 3, The transfer function for a 10-stage RC filter is as follows. I've got 10 poles ranging from minus 39 to minus 0.42. The A matrix looks like the following. Negative on the diagonal, meaning if I add voltage at any node, the current flows away. On any given node, 10 units of current go left, 10 go right, and the extra 0.2 went to ground through the 50 ohm resistor to ground. If you look at the eigenvalues of that A matrix, those are exactly the same as the poles. So again, eigenvalues tell you how it behaves. I've got a slow mode, something decays to e to the minus 0.42t, and something decays to e to the minus 39t. The eigenvectors tell you what behaves that way. A is a 10 by 10 matrix. It has 10 eigenvalues. It also has 10 eigenvectors. So if you look at the fast eigenvector, that would be like negative voltage, positive, negative, positive, negative, positive. If you have that zigzag pattern, very quickly the voltages go to 0. And they go to 0 as e to the minus 39t. If I take the slow eigenvector, it starts out small and slowly increases in voltage. There, that decays to e to the minus 0.42t. And you can see that in MATLAB. For example, under heat, this is a dynamic simulation of that RC system. If I make the initial condition V on line 3, make the forcing function 0, change the initial condition, I can sit there and watch the natural response. So let's do that here in MATLAB. So here's the program heat. What I do is I make the initial voltages 0, my step size, time equals 0, and I'm going to find the step response. So the voltage on the left will be 1. I'm going to run for 5 seconds. Here's my differential equations. At any given node like V2, V2 dot is 10V1 minus 20.2 V2 plus 10 V3, and so on. The oddity is this last node. Since there's only one resistor attached, it's only 10.2. Integrate and plot. So when I plot the response, this is the step response of the system. And you can see I have the left side goes to 1 volt, and very slowly the RC circuit starts charging up. This is also the heat equation. To make the left side 1 degree, very slowly the rest of it starts warming up. So that's the step response. Let's look at the natural response for eigenvalues and eigenvectors. So let's look at the fast eigenvector. If I make the initial condition, the fast eigenvector, scaled so the peak is 1, this graph's better, make my forcing function 0, and then run it, what I see right here is the response. Poof, gone. That decayed as e to the minus 39t. To slow it down, let's make the step size go 10 times slower so you can see what's happening. Maybe just run for 50 milliseconds. If I run it, notice the shape. The shape is the eigenvector. The shape stays the same. The eigenvector stays the same. I'm going to run it for a little bit longer. Put 1 second. But the amplitude drops. The amplitude is decaying as the eigenvalue. That was e to the minus 39t. And only that one eigenvector is excited because my initial condition is equal to an eigenvector. So that's the fast eigenvector. Now, instead make the initial condition the slow eigenvector. So this is the slow one scaled, so the peak is 1. If I run that, the shape is the eigenvector. The amplitude is the eigenvalue. This is decaying as e to the minus 0.49t, really, really slow. And with that slow size, not a whole lot's happening. If I speed it up some, and let's let it run for 2 seconds. You can see the shape stays the same. The shape is the eigenvector. The amplitude is dropping, however. This is dropping as e to the minus 0.49t. So that's the slow mode. And there's also 8 other eigenvalues, eigenvectors. Here's a question for you then. Suppose my initial condition is something random. What happens? Well, let's try it. If my initial condition is something random, just 10 random voltages, and I run it, that's what happens. I'm going to get a different response every time because it's random. But notice this shape. We just saw that shape. This is the slow eigenvector. What's happening is I've got 10 modes. It's a 10th order system. I've got 9 fast modes, 1 slow mode. The fast modes quickly go to 0. Let's try that again. Fast modes quickly go to 0, leaving the slow mode. What you're seeing is an eigenvector. That's the eigenvector associated with the slow mode. So let's get an illustration of what eigenvalues and eigenvectors are. Eigenvalues tell you how it behaves. In this case, the slow mode is decaying z to the minus 0.49t. The eigenvector tells you what behaves that way. This shape decays e to the minus 0.39t. Plus there's a whole bunch of other modes. Those very quickly went away, leaving the slow mode, leaving the dominant mode. There's also one thing kind of impressive about MATLAB. MATLAB is not designed for animation, but it does a pretty good job at it. So again, as I mentioned, there's the fast mode, slow mode. Here's the slow mode. Here's the fast mode. And here's a random initial condition in red. The random initial condition quickly decays into the slow mode. So in summary, very few people understand what eigenvalues are. Even fewer understand eigenvectors. The nice thing about electrical engineering is you can actually see an application of it. The heat equation is a very good example. With the heat equation, eigenvalues, eigenvectors mean something physically. The eigenvalues tell you what or how the system behaves. Eigenvalues are poles. Eigenvectors tell you what behaves that way. If you want to know what decays quickly, look at the fast eigenvector. If you want to know what decays slowly, look at the slow eigenvector. For the rest of the course, we'll only be looking at eigenvalues. Specifically, we'll look at the dominant pole. If the dominant pole is stable, that tells me the system's stable. If the dominant pole has a 2% settling time of 4 seconds, then worst case, the system also has a 2% settling time of 4 seconds. But there's also eigenvectors that we'll kind of ignore the rest of the semester. Again, not that many people understand what eigenvectors are, but they are kind of useful if you want to understand a system. Eigenvalues are poles. We'll look at mostly those from now on. So that's lecture number 4 for ECE 463 Modern Control, Eigenvalues and Eigenvectors.